Okay, let's unpack this. We've all seen it, right? You click something on a website, maybe it needs to fetch data, but you still expect the page to, work.
Yeah.
But JavaScript itself is single-threaded. So how on earth does it handle things like network calls or even just waiting for a click without, completely locking at the browser?
That's the core question, isn't it? If JavaScript literally had to wait for every slow operation, browsing would be painful,
Yeah.
completely unresponsive tabs.
Right.
The magic behind it all, what lets it juggle, is the browser event loop. That's what we're digging into.
The event loop. Okay. So it's the system that makes this single thread feel like it's multitasking.
Precisely. It's like the traffic controller. JavaScript itself doesn't become multi-threaded, but the event loop works with other browser parts to manage these slow tasks off to the side.
Off to the side.
Yeah, and it brings the results back in an orderly way. We need to look at the main players. The call stack, web APIs, the queues, there are a couple of those, and the event loop orchestrating everything.
Got it. Let's start with where the JavaScript code actually runs, the call stack.
Exactly. Think of the call stack like a to-do list for functions. Your synchronous code executes here, one function call at a time. Call a function, push it on top, function finishes, pop it off.
Simple enough.
But if that stack isn't empty, if there's code running on it, the browser's main thread is busy. That's blocking. If something takes too long there, everything else just stops. No rendering, no clicks processed, nothing.
Okay, so the call stack is the bottleneck, potentially. How do we get time-consuming stuff like that data fetch or waiting for a timer off the stack so it doesn't block?
That's where the browser environment helps out with web APIs. These aren't technically part of JavaScript itself, but features the browser gives you.
Like set timeout or fetching data?
Yep, set timeout, fetch, even things like add event listener for clicks. When your code calls one of these, it basically says, hey, browser, handle this, and hands the task off to the appropriate web API.
So it delegates.
It delegates the waiting or the background work. The JavaScript code itself just moves on immediately to the next line. The web API handles it somewhere else, outside the call stack.
Okay, so the browser's doing the waiting now. What happens when it's done? Say the timer finishes or the data comes back.
Yeah.
Does it just interrupt whatever JavaScript is running?
No, absolutely not. That would cause chaos. When the web API finishes its job, it doesn't barge back in. It takes the callback function you provided the function meant to handle the result and places it in a waiting line, a queue.
Right, the queues. I've heard things can get a bit tricky here, like there are different queues. Why more than one?
Good question. Yes, there are two main ones we care about, and the difference is crucial. First, you have the microtask queue. Think of this as the express lane, high priority.
Okay.
This is mainly for callbacks related to promises, specifically when they settle so, the functions you pass to then .catch, or finally, they end up here.
And the other queue, not the express lane.
That's the callback queue, sometimes called the macrotask queue. This is the standard waiting area for most other asynchronous stuff. Callbacks from set timeout, set interval, user interaction events like clicks, network I/O callbacks often land here.
And there's a strict order. Microtasks always go first.
Always. This is key. The event loop gives absolute priority to the microtask queue. Before it even considers pulling something from the callback queue, it will run every single task currently waiting in the microtask queue until it's completely empty.
Wow. Okay. So tell me about the event loop itself. What's its actual job in managing all this?
Its core job is surprisingly simple, but nonstop. It perpetually asks one question. Is the call stack empty?
And when the answer is yes.
Yeah.
When all the synchronous code is done.
Right. If the call stack is empty, the first thing the event loop does is check the microtask queue. If there are tasks there, it takes them one by one, pushes them onto the call stack, and they run. It keeps doing this until that microtask queue is totally clear.
Only then does it look elsewhere.
Only then. Once the microtask queue is empty, the event loop checks the callback queue, the macrotask queue. If there's a task waiting there, it takes just one, the oldest one, and pushes it onto the call stack to run.
Just one from the callback queue at a time?
Generally, yes.
Yes.
It takes one, lets it run, and then the loop starts again. Check stack, check microtasks, check macrotasks. Also, between these checks, usually after handling a macro task, the browser might decide to do rendering updates like repaint the screen.
That whole cycle, check stack, empty microtasks, handle one macro task, maybe render. That's how it keeps things moving without freezing.
That's the essence of it. It allows asynchronous operations to complete and their handlers to run without blocking the main thread indefinitely.
Okay, let's try that classic example. Say I have a set timeout with 0 delays, which should run immediately, right?
Theoretically, yes. as soon as possible.
And right after that, I have a promise that resolves instantly, and I attach a dot, then callback. Which callback function actually runs first, the set timeout one or the promise one?
Perfect example. The set timeout callback goes into the callback queue, macro task queue. The set callback from the instantly resolved promise goes into the microtask queue.
Oh.
So, assuming your initial script finishes and the call stack becomes empty, the event loop checks. Microtask queue first. It finds the promise callback and runs it. Then, on the next cycle potentially, it will check the callback queue and find the set timeout callback. So the promise callback runs first, even though the timer was set for immediately.
That really highlights the priority. Understanding that queue difference is huge.
It absolutely is. This isn't just theory, it's practical knowledge for writing smooth web apps. When your UI feels sluggish or some callback isn't firing when you expect, tracing how the event loop, the queues, and the call stack are interacting is often the key to debugging it.
So knowing this helps you avoid blocking the main thread and write code that feels more responsive.
Exactly. It helps you structure your asynchronous logic better, leading to more performant and predictable applications. It's fundamental stuff for web development.
So in essence, this event loop is this constantly running process, checking the stack, prioritizing these micro tasks, giving the regular callbacks a turn, all to keep that single JavaScript thread from getting stuck.
You got it. It's the elegant solution to the single-threaded problem. And, thinking about that loop spinning, imagine a user clicking rapidly while network data is arriving and maybe an animation needs to update the screen. How does the loop juggle all of that? Which things get delayed slightly? What does that whole dance mean for how responsive your app actually feels? That's something worth chewing on.